Euclid's division lemma actually might seem very simple. It is a very fundamental concept, okay, and we have been using it for a while. But today we would look at its intricacies. Why is it so important concept in number theory? And of course, we'll go on to prove it. Okay, so it might you might take it for granted. You might think that it is just there, but today we'll see that it can be proved pretty rigorously. So to begin with, let's write in a form of an equation what does the lemma say? It tells us that for two integers a and b, okay, so there are two integers a and b. That's what it is said here. A and b are element of I, which is an integer. So they are both integers. We can find two numbers q and r such that a is equal to qb plus r. Now, of course, in this particular equation, the numbers q, r, a, and b have certain properties, and let's just put it down. As I already said, in the most general case, a is an integer, b is an integer, q is quotient, and of course, this is allowed to be an integer. It can be any integer, and r has properties such that r is always less than b, but at the same time r is greater than or equal to 0. Okay, so r is always less than b. Okay, so now in common terms, in common parlance, so far if you look at it, this q is nothing but quotient of a division and r is nothing but the remainder when a is divided by b. Let's take a simple example and understand this equation. Okay, let's take a very simple example. Let's say that my two numbers a and b are 10 and 3. Okay, forever, okay, for a while now we have been doing division of such natural numbers. So let's try to divide our number a by b. Of course, this is simple. Okay, so this is b, or in our case this is just 3, and this is a, okay, or 10 in our case, in this specific example. So let's try to divide, see what happens. What are we actually doing? We'll say 3 ones are 3, 3 2s are 6, 3 is 9. So we'll go on repeating the table of 3 until we reach a number which is the largest possible number less than 10. Okay, so in this case, in case of 3, the table of 3, 3 3s are 9. So 9 is the largest possible number in the table of 3 which is less than 10. And as soon as we reach that number, we write it here. Okay, the quotient goes to the top, the number comes here, and we say 10 minus 9, and we write the remainder as 1. So this is the process of division. This 3 is nothing but the quotient q in our equation. This is the q, and this 1 is nothing but remainder r. Okay, and in our case this is the remainder comes here in our equation in the division lemma. And the r, of course, has a special property that this r is always less than b. Okay, so this remainder is always less than the divisor, right? So the 1 is less than 3. If it were not, then we could have gone one more step, right? Instead of dividing it by 3, we would have divided it by 4, right? So that is the quotient would have been 4. So this is what our division lemma states, and this is how we understand it. Of course, for our special case, okay, for our special case, we only took the number b to be an natural number. It is greater than 3, but in most general case it can be any integer such that it is not equal to 0. So this b cannot be equal to 0 because division by 0 is not defined. Now let's take an example of a negative number, right? So we took an example of a positive number right here. Our b, we took it to be 3, and let's now take an example of a negative number and again understand how this division lemma actually works. So this is our equation qb plus r. Now let's take b to be equal to minus 3. Again the same thing we'll do. Okay, we'll try to find q and r for various values of a. So let's take the first value of a, which is 10. How can we construct? What is the possible method for constructing the number 10 such that this r is greater than 0 but less than b, so less than the absolute value of b, so less than 3. So how would we do that? We would say that the quotient, one possible value of quotient can be minus 3 into minus 3, so that is equal to minus that is equal to plus 9. Okay, so minus minus become plus, so this becomes plus 9, and we are left, right? So remember, this r has to be plus 1. So if you notice, what are we doing here? We are starting from number 0. Okay, let's just write it down. These are all the multiples of b. Okay, so in our case b was minus 3. These are all the multiples of b. Various values of q allow us to reach these multiples, right? This is what we are saying. If I multiply this b minus 3 with minus 1, I reach 3. If I multiply by plus 1, I reach minus 3. Similarly, the various values here, if I multiply by minus 2, I reach 6, and plus 2 would get me to minus 6. So the various values of q allow us to reach the multiples of b, and then the remainder allows us to fine tune the result. So to get any number, any integer between minus 6 and minus 3, we would use the remainder. Similarly, this remainder would allow us to cover this range. Similarly, the remainder would allow us to cover this range in such a way that this r is always positive. So r would always take us from left to right. Okay, so this is what r would do. We'll go back and then r would take us in the positive direction. Let's take another example. Let's say how we can create minus 8. So to create minus 8, first we would have to go to minus 9. So we'll go to minus 9, which would happen if we multiply minus 3 with 3. And then, of course, minus 9 is not the number. So we take one step forward, and our remainder would be plus 1, or this would be plus 1. Okay, so this r would be 1, and of course our q would be 3. Okay, so this remainder always has to be positive, and that is very important. That is an important concept. Similarly, if I were to wanted to construct just the number 2, so look, if you look at it, the 2 falls between 0 and 3. So I would use the value of 0 as q, and then I would just use the value of r as 2, and then I would be able to reach 2. Right? So this is how this lemma actually works. This is what this lemma is telling us. The important thing is, it is saying much more than this special case, right? It is saying much more than the division itself. So you can divide 10 by 3 and then say that the quotient would be 3 and the remainder would be 1 in that special case. But Newton's division lemma, it is telling us that this would work for every case. No matter what a and b you pick, it would just work. It is telling us why that division actually works. And in the next section, we would see a rigorous proof of why this division lemma applies for all integers. A lot of students have trouble visualizing or picturizing how the Euclid's division lemma actually works. So let's try to draw a picture to better understand this division lemma. Before that, we will write down the division lemma and see if we can make some sense out of it. So A is equal to QB plus R. It tells us that for any two integers A and B such that B is not equal to 0, I can always find two numbers Q and R, where Q is an integer and R is always between B and 0. Of course, R can also be 0. Okay, so that's what Euclid's division lemma tells me, that I would always be able to find a quotient and remainder for any two numbers, and the remainder would always satisfy this property. So it is a very strong statement that such a remainder would always exist. Let's take an example to understand why such a remainder always exists. Let's just look at the division process and see if we can understand why our remainder would always exist. So here I am drawing two numbers. One is my a, which is of course the dividend, and let's take it to be 8. And the second one is my divisor or b, and let's take it to be equal to 3. So these are my two numbers. I am trying to divide 8 by 3. So what would I do? I'm trying to remove as many 3's as possible from this number 8. That is my entire object. That is the process of division. So first I remove one 3, then I remove another 3. After I remove the first 3, okay, so the first 3 is gone. I am left with 5. So this is the 5 remaining. And as soon as you look at 5, you say that, oh, there is one more 3 inside it. So probably I can remove that also. So I remove the second 3. And now I am left with just this, which is 2. So I am left with just 2. Now in this 2, from this 2, I cannot take any more 3's. So the process of division stops here. And of course, because we are stopping the process of division, I cannot remove any more 3's from this 2. This remainder, this 2, has to be less than b. Okay, so from the very nature of the division process, we understand that we should be able to obtain a remainder which is less than b. In the case of natural numbers, like you are seeing, it is pretty obvious that this remainder would exist. In the case of integers, it's not so trivial. But let's just write down two inequalities which would help us focus on negative numbers as well. So if you look at it, what we have done here is that our quotient came out to be 2. Okay, so that is our quotient, 1 and 2. So that is q is equal to 2. And our remainder, of course, came out to be also 2. Okay, that's a different thing. Let's not look at the remainder now. Let's just focus on this quotient first. So what is quotient into b? Quotient into b is qb, which is equal to 2 into 3, which is equal to 6. Okay, that is what it is in this case. If you look at it, this qb is always taken as high as possible. So we increase our quotient. Okay, we start from 1, we go to 2, we go to 3. We increase our q, okay, one by one, until our qb becomes maximum possible, so that qb is less than a. Okay, so qb is increasing, but we don't increase it so much that it becomes bigger than a. It has to be less than a. So here I take my q, I start from 1, then I take it to 2, and then I stop, because the next q, if I did q plus 1 into b, it would be 3 into 3, which is equal to 9. So that would of course be bigger than my a, which is 8. So I don't do this. I stop right here. I take the largest possible value of qb, which would be less than a. By the very extension, the very next value of q would take us above a. So these are the two important inequalities which would allow us to sort of work with negative integers. Okay, with negative integers, a little bit complicated, but of course they are not insurmountable. Just like any other problem, they are also surmountable. So now let's take an example of negative integer. Here, let's say that my a is equal to minus 10. I can take a to be whatever I want. Okay, I can take a, I can even take it negative. There are no restrictions on the value of a. We said that it could be integer, it could be any integer. And I keep my b to be the same. I keep my b to be equal to 3. Now I have to choose a value of q such that qb is less than a. Okay, so the qb should come out to be less than a in negative terms. Okay, so I choose a value of q, and at the same time q plus 1 into b, okay, q plus 1 into b should come out to be greater than a. So both of these should hold. So I take a value of q equal to minus 4. Okay, let's see what happens with this value. Okay, I will try various values, just like we did in this division. Okay, in this division also, in positive we started from 1, 2, 3. Similarly here also I will start from, but I'll try various values, and I just say that I chose the value of q equal to you'll see that it's a fortunate value choice, but again we'll choose the value of minus 4 and see what happens. For value of minus 4, qb comes out to be minus 12, and this minus 12 is of course less than minus 10 in negative terms, sorry, minus 10 in negative terms, right? So this is more negative, so of course it is smaller. What is the value of q plus 1b? This comes out to be minus 4 plus 1. Okay, so q plus 1 is minus 4 plus 1, which is minus 3. So this becomes minus 3 into, of course b is 3 still, so this becomes minus 9. And now my minus 9 is nothing but bigger than minus 10, because we are looking at negative numbers. So minus 9 is towards the 0, so it is bigger than minus 10. So at this point I can say that both my inequalities, this and this, are satisfied, and therefore the value of q that I need to choose is equal to minus 4. So we proceed with that value of q, and now we find the remainder r. R is nothing but a minus qb. Okay, that has always been the case. Here also the r is nothing but a minus qb. So a is 8 minus 6, which is equal to 2, right? So r is nothing but a minus qb. That is the case here also. So here a is of course our minus 10, minus qb is minus, will remain here, and qb is of course negative. We said that it is minus 12, so this comes out to be minus 12, and so our answer becomes minus 10 plus 12, which is equal to plus 2. So like we said that even in case of negative numbers we can arrive at a positive remainder if we choose the value of q properly. Another change which we need to do if we are choosing b to be negative, okay, b can be negative also, is that we put an absolute value sign here, indicating clearly that our remainder is always has to be positive. Hope this helps in visualizing division lemma. If not, if you still have doubts, don't hesitate to put them in comment section below. Thank you. Now let's look at the proof for Euclid's division lemma. Before we start the proof, let's try to motivate it somewhat, because we have been doing divisions for a while now, and that's not really clear. Why do we need to prove anything that has to do with division? So here's an example of a division. I know 3 times 3 is 9, and this leaves a remainder of 1. So I get a quotient of 3 and a remainder of 1 when I divide 10 by 3. So 10 is of course my a and my b is 3. Okay, so here I was able to do the division without proving this lemma at all, without knowing whether this lemma is true or not. So why do we indeed have to prove this lemma at all? Why do we need that? See, think about it this way. This division, we have been doing it successfully for a while, okay, and it seems to work for all possible combinations of numbers. No matter what two values of divisor and dividend I choose, it always seems to work. This division lemma tells us why it works. Okay, it tells us that for all possible values of a and b, as long as they satisfy certain conditions, I would always be able to find q and r, and the value of r would be such that it is greater than or equal to 0 and it is less than b. So this is what this lemma is telling us. It is a very strong statement, while the individual divisions, they are a special case. Okay, so think of it this way. This is a very strong statement. Of course, we said that there are certain properties of this a, q, b and r that these a, q, b and r should satisfy. This a could be an integer, q is allowed to be an integer no matter what, r we said would be between 0 and b, and b for the first case. Okay, let's initially only prove this lemma for when b is greater than 0. We would subsequently extend this b to include all possible integers except 0. B can never be equal to 0 because division is not defined for b equal to 0. Okay, first we will do it for b greater than 0, then we will do it for b less than 0, and that would complete our proof of Euclid's division lemma. Before we start the proof, let's understand what the nature of this remainder r is. This r is of the form a minus qb. Right? This is very simple, a minus qb, that is equal to r. This qb, we take it in this case, right? In any case of division, we make this qb to be as large as possible. We try to increase the value of this QB and we make it maximum to the extent that our remainder does not become negative. Okay, so this remainder has to be positive. I don't choose the value of QB very high, okay, in such so high that the remainder becomes negative. I don't choose the value of QB any lower than it has to be. Okay, so for example, in our division of 10 dividing 10 by 3, I did not choose the value of QB to be equal to 6 or 12. 12 of course would have been too high and my remainder would come out to be negative. 6 would have been of course too low and my remainder would be 4, which is greater than 3. So there is one more 3 hidden inside this 4, which I should have removed. So this 6 would have been, this is QB, right? This QB value of 6 would have been too low. The QB value of 12 would have been too high. I chose the value of QB so high, highest possible value, in such a way that the remainder R remained positive. I took it so as high as possible while keeping the remainder is still positive. Okay, this is the value of QB. So QB I am trying to make it maximum in such a way that A minus QB is positive, which means that A minus QB, since QB is maximum possible value, it means that A minus QB is the minimum possible value, minimum possible positive value. Okay, this is the nature of our remainder R. From this nature, let's try to derive a set S of all possible values A minus xb, where x is an element of integers, okay, and A minus xb is defined to be only positive values. So this particular set S contains all A minus xb, where x is an integer for x, and A minus xb is also positive. It contains all such values. So let's try to choose some values of x. For example, when I choose the value of x to be equal to 0, this comes out to be A. So my A would be in the set S. I'm enumerating some values in the set S. A plus B, when I chose x to be minus 1, A plus 2B, and on the other side I would have A minus B and A minus 2B. Okay, so these are some of the values. Okay, there are more values on either side. These are some of the values that I have enumerated from my set S. My remainder R, set S is all possible positive A minus xb. So of course my remainder R would belong to this set S. Not only would it belong to the set S, we have also shown that it would be the minimum, because all positive values A minus xb reside in the set S, but my R is the minimum of those values. Okay, so I would have to pick the minimum value from this set S. That minimum value would nothing be but R. Okay, if R can be picked out from set S, I have proven the Euclid's division lemma. I have shown that a value R exists in set S which is positive and minimum, and hence I have proven that Euclid's division lemma is true. Okay, so in order to prove that value R exists in set S, I would show two things in set S. I will write down the set again, A minus xb. The first thing that I am going to show, that I need to show, is that this set A minus xb, this set actually has at least one element. It is guaranteed to have one element. If it does not, if it's not guaranteed to have one element, let's say the set S can be empty, then my R of course cannot exist, and the Euclid's division lemma becomes false for those two particular values of A and B. Okay, so set S necessarily has to be non-empty for R to exist. Okay, so if I can show that at least one value of for one value of x, I can get a positive answer. That value would lie in set S, and set S would become non-empty. So I chose the value of x to be equal to minus A. In that case, A minus xb becomes A plus mod of A into B. If you look at it closely, this B is guaranteed to be greater than 0. Therefore, this is guaranteed to be positive, okay, because mod of A is always positive. So this is guaranteed to be positive. Not only is it guaranteed to be positive, even if A is negative, my mod A B is greater than A, and therefore this entire thing is guaranteed to be positive. Okay, because mod A of B is always greater than A and it is always positive, A plus mod A of B is always positive, which means that it would lie in my set S. So for this particular value of X, I can always find an element which is positive and which lies in the set S. So set S is necessarily always, for all possible A's and B's, non-empty. That is the first thing that I have shown. The second thing I am going to show is that it is indeed possible to pick out a minimum value from this set S. If set S was such that minimum value cannot be picked out, then I cannot pick out R, which is the minimum value. Okay, then if I cannot pick out R, then Euclid's division lemma becomes false. So I'm going to show that this set S, I can always pick out a minimum value from this set S. If you look at this very closely, set S consists of just integers, a minus xb, they are just integers. For all integers, if they are in a set, there is a theorem known as well-ordering theorem, which tells us that if a set consists entirely of integers, then it's always possible to pick out a minimum and a maximum value from that set. So here's an example. This is a set which consists of integers, and you can obviously see that from that set I can always pick out a minimum value. Since my set S also consists of just integers, by well-ordering theorem, I am saying that I can pick out a value R which is minimum from this set, the minimum value from this set, and that value is R. That value R is minimum and it is positive, and therefore that value R is nothing but our remainder in R is equal to A minus QB. So here with these two properties, right, the well-ordering theorem and non-emptiness of set S, with those two we have shown that the R exists, a minimum value R exists. Now we need to show that this minimum value R, which we have picked up from the set, is between 0 and B. And how are we going to prove that? Let's suppose that this R is greater than B. So we are using contradiction here, proof by contradiction. In that case, I can write R is equal to R dash plus B 100%, because R is greater than B. So I can write that, where R dash is always positive. Okay, this R dash would always be positive. Now I substitute this R dash in our original equation. I can write R dash plus B is equal to A minus QB, which gives me R dash is equal to A minus Q plus 1 B, which is equal to nothing but A minus Q dash B. Therefore, not this R dash is positive and it is also of the form A minus XB, and therefore it should lie in our set S. Okay, this R dash should be an element of our set S. Remember, what did we say initially? We said that we are picking out this R. This R that we are picking out was the minimum value from this set S. That was the definition. By definition, R was the minimum value from this set S. But now we have shown another value R dash which is less than R. Okay, from this equation we are saying that R dash is less than R. We are showing another value R dash which is less than R, and this R dash also belongs to our set S, and therefore there is a contradiction. Our R is no longer the smallest value. We picked up the smallest value, but it is not the smallest value. Therefore R cannot be greater than or equal to B. This is incorrect, and R has to be between 0 and B. If R was indeed greater than B, there is some other R dash which we should have picked up from the set S. So this is another thing, another property that we have shown, that R is greater than R is between 0 and B. The second property of R and Q that we are going to show is that R and Q are unique. What does that mean? It means that R is equal to A minus QB. Here R and Q are unique. Again, let's use proof by contradiction. Let's try to prove it by contradiction. So we assume another value of R dash and Q dash which also satisfy this equation. Okay, so not only is this R and Q satisfying our equation, but also R dash and Q dash also satisfy this equation. Now let's subtract these two equations. We would get R minus R dash is equal to A and A would cancel out, and here we would get Q dash minus Q into B. What can be said about R minus R dash? Let's try to understand that. See, both R and R dash satisfy the relation that R comma R dash, they are both less than B. Okay, they are both lie between 0 and B. What does that mean? It means that my R minus R dash, this R minus R dash has to lie between minus B and plus B, because R and R dash lie between 0 and B. So R minus R dash necessarily have to lie between minus B and plus B, which means that my Q dash minus QB, this thing has to lie between minus B and plus B. So that is what I am going to write. Has to lie between minus B and plus B. I cancel B from all over and I get Q dash minus Q lie between minus 1 and plus 1. Of course, Q dash minus Q is an integer. Therefore, what am I saying? I am saying that this Q dash minus Q, right, the only integer between minus 1 and 1 is 0. So therefore, Q dash minus Q has to be 0, which means that Q dash is equal to Q. In turn, we are showing that our Q dash and Q are not two distinct variables, not two distinct values, but a single value. And in turn, this R and R dash are not really two distinct values, but a single value R. Okay. So with this, we complete our proof of Euclid's division lemma. We have shown that there is a unique value of R which exists, which satisfies this relation. Okay, that R lies between 0 and B for all possible positive values of B. Okay, and that was the intent of this Euclid's division lemma. Now, as we said before, in this case, in this particular proof, we have taken the value of B to be equal to greater than 0. Now let's prove the same division lemma on the other side. Let's assume that B is less than 0 and try to prove it. Okay. So in that case, I would write A is equal to Q dash B dash plus R. Here B dash, we are saying, is less than 0, which means that it is negative. Therefore, I can write B dash to be equal to minus B, where B is greater than 0. Okay, I can write it. Now I substitute this B dash here. I get A is equal to minus Q dash B plus R, where B is of course greater than 0. Remember, even in our initial proof, we never restricted the value of Q. We allowed it to be full integer range. We allowed it full integer range. So it could very well be negative as well. And therefore, I can write Q dash minus Q dash to be equal to Q plus R, where B is greater than 0. Okay. This particular case we have already proven is true. Okay, and we have shown that these two forms where Q dash, where B dash is actually negative, okay, these two forms are exactly equivalent. They are equivalent. Okay, which means that this is true and therefore this is also true. Okay, this is proven and therefore by extension this is also proven, because those two are exactly equivalent. And with that, we have proven our Euclid's division lemma for all possible values of b, where b is not equal to 0 and b is an integer. That completes the proof of this division lemma. Hope it was clear. Hope you were able to take something away from it. If not, if there are any doubts, then please mention them in the comment section below. I will try to clarify them in a subsequent class. Thank you very much.